General properties of the transition elements D block. Their properties are intermediate between S block elements and P block elements. They are more electropositive than P block elements but less electropositive than S block elements. All transition elements are all metals. They display high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. Melting points. In any series, as we move from left to right, the melting points of these metals rise to a maximum at D5 except for Mn and Tc and fall regularly up to D10. Enthalpy of formation. They have high enthalpies of atomization. The metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. Variation in atomic and ionic sizes. When we move left to right in any series, the nuclear charge increases. In general, radii of ions having same charge in a given series decrease with increasing atomic number. The atomic radii of a given series also show the same trend in variation. The curves show an increase in radii from the first 3D to the second 4D series of the elements. The radii of the third 5D series are nearly the same as those of the corresponding members of the second series. This is due to the filling of 4f before 5d orbital, which causes a regular decrease in atomic radii called Lanthanoid contraction. Ionization enthalpies. Ionization enthalpy increases along each series from left to right. The magnitude of the increase in the second and third ionization enthalpies for the successive elements in general is much higher. The lowest common oxidation state of these metals is +2. In general, the third ionization enthalpies are quite high. For copper, nickel and zinc, it is difficult to exhibit +3 oxidation state. Oxidation states. There is a very small energy difference in between n-1d and ns orbitals. As a result, electrons of n-1d orbitals as well as ns orbitals take part in bond formation. Therefore, transition elements show variable oxidation states in their compounds. The participation of ns electrons in bonding leads to +2 oxidation state, which is a lower oxidation state. The participation of n-1d electrons in bonding leads to higher oxidation states like +3, +4, +5, +6, etc. These oxidation states depend upon the nature of combination of transition metals with other metals. The elements in or near the middle of the series exhibit the greatest number of oxidation states. Manganese for example, exhibits all the oxidation states from +2 to +7. Other examples are Ti +2, +3, +4, Cr +1, +2, +3, +4, +5, +6, Cu +1, +2. Scandium Sc does not exhibit +2 oxidation state. The variability of oxidation states is due to incomplete filling of d orbitals in such a way that their oxidation states differ from each other by unity. The only oxidation state of zinc is +2. No d electrons are involved. Titanium 4 is more stable than Ti3 or Ti2. Magnetic properties. Elements with unpaired electrons behave as paramagnetic substances. These substances are attracted by the magnetic field. The transition elements that contain paired electrons behave as diamagnetic substances. These substances are repelled by the magnetic field. The paramagnetic character increases as the number of unpaired electrons increases. Formation of colored ions. Most of the transition elements form colored compounds both in solid state as well as in aqueous solution. When an electron of a transition element is excited from a lower energy d orbital to a higher energy d orbital by absorbing the light energy, it shows color. The color observed corresponds to the complementary color of the light absorbed. For example, Cu2+ are bluish-green in color due to absorption of red light wavelength. As Zn has completely filled d orbitals, it cannot absorb radiation and hence Zn2+ sols are white. Formation of complexes. Transition metals form many complex ions. This is due to the comparatively smaller sizes of the metal ions, their high ionic charges, and the availability of d orbitals for bond formation. They are the electrically charged complexes with a metal ion in the center, which is surrounded and linked by a number of neutral molecules or negative ions. A few examples are FeCN6 whole 3 minus, FeCN6 whole 4 minus, CuNH3 4 whole 2 plus, and PtCl4 whole 2 minus. Catalytic properties. The first row transition elements exhibit catalytic properties due to the presence of unpaired electrons which can form complexes. Vanadium 5 oxide in contact process, finely divided iron in Haber's process, and nickel in catalytic hydrogenation are some of the examples. Formation of interstitial compounds. An interstitial compound is formed when an atom of sufficiently small radius, such as H, C, or N, sits in an interstitial hole in a metal lattice. All the first row transition metals form interstitial compounds with the elements of the S and P blocks. The principal physical and chemical characteristics of these compounds: 1. They have high melting points, higher than those of pure metals. 2. They are very hard. Some borides approach diamond in hardness. 3. They retain metallic conductivity. 4. They are chemically inert. Alloy formation. As the D block elements have nearly same atomic sizes, they can easily take up positions of one another. This causes alloy formation. For example, chromium, vanadium, tungsten, molybdenum, and manganese are used for the production of a variety of steels and stainless steel.